Earth's ability to support life depends on a number of characteristics. Its position within the solar system places Earth at a distance from the Sun that keeps the Earth within the temperature range in which life can thrive. Among other things, the temperature of Earth is within the range needed to have liquid water. This is essential as all life on Earth depends on the availability of liquid water. But just getting enough energy from the Sun is not sufficient. In fact, if all of the energy arriving from the Sun made it to the surface of the Earth, it would be a very inhospitable place. For life to survive on Earth, the high-frequency ionizing radiation and very high-energy charged particles emitted from the Sun need to be filtered out before they reach the surface of the Earth. This occurs in two ways. First, the Earth is surrounded by a magnetic field. This large field, thought to be generated from convection of iron and nickel in the liquid portion of the Earth's core, deflects much of the high-energy charged particles from the Sun. If these particles did reach the Earth, they would have enough energy to strip away our atmosphere, leaving the planet uninhabitable. In addition to the deflection of charged particles by the Earth's magnetic field, gases in the atmosphere also help by filtering out shorter wavelength, ionizing ultraviolet radiation, allowing only lower energy, mostly non-ionizing radiation to reach the ground. These factors, which allow enough energy through to create temperatures conducive to life while filtering out the highest energy, most damaging radiation, create the conditions for life as we know it. The role the atmosphere plays in filtering out ionizing radiation can be seen by comparing the profiles of energy that arrive at the top of the atmosphere, shown here in yellow, and profiles of the energy that reach the surface, shown here in red. The mostly short wavelength ionizing radiation is filtered out mostly by oxygen in the stratosphere. The fact that the filtering out of this ionizing radiation depends on the presence of oxygen points out an interesting observation. Life produces the oxygen that helps maintain the conditions that support life. It wasn't always this way. The atmosphere we have today is thought to be Earth's third atmosphere. In the very early period of the planet, just after its formation 4.5 billion years ago, the planet was very hot due to energy associated with its formation as well as from heat produced by the decay of many short-lived radioactive isotopes. During this time, the atmosphere is believed to have been made up primarily of light molecules such as hydrogen and helium gas. Over time, as the Earth cooled, these low molecular weight gases were lost to space, while other gases released from the interior of the planet through volcanic activity created the second atmosphere, containing many gases, including large amounts of water vapor, carbon dioxide, sulfur dioxide, hydrogen, and nitrogen, as well as other reduced compounds such as ammonia and methane. There may also have been small amounts of oxygen present, formed by sunlight reacting with water vapor, but the concentrations were nothing like what we have today. Due to the relatively high concentrations of greenhouse gases such as carbon dioxide and methane, as well as the heat released from the planet itself, atmospheric temperatures were probably much higher during this period compared to today. As more and more water accumulated on the surface of the Earth, it condensed in large quantities and formed the oceans. Geological evidence suggests that this happened about 3.8 billion years ago. As the oceans formed, gases in the atmosphere began to dissolve into the water, changing the composition of the atmosphere. In particular, the oceans probably absorbed large quantities of carbon as carbon dioxide dissolved in the oceans, then combined with water to form carbonic acid, which could then be fed into the carbonate buffering system, allowing the oceans to help lower the concentration of carbon dioxide in the atmosphere. The concentration of gases in the ocean and atmosphere probably reached an equilibrium over a few million years, and this second atmosphere, with almost no oxygen and relatively high concentrations of greenhouse gases, persisted for over a billion years. Then something remarkable happened. About 2.5 billion years ago, life arose, and once it did, small microscopic plants called cyanobacteria evolved photosynthesis, which is the ability to combine carbon dioxide and water to form sugars, using energy from the sun to drive the reaction, thereby storing the solar energy as chemical energy contained in the bonds of the sugar molecules. As a byproduct, this reaction produces oxygen. Oxygen is a very reactive molecule, and for a long time, the oxygen produced probably quickly reacted with abundant reduced compounds in the atmosphere and in the oceans, preventing oxygen from accumulating in the atmosphere. But eventually, as photosynthetic bacteria spread throughout the oceans, enough oxygen was produced to allow it to start accumulating, changing the composition of the atmosphere towards one that is more like what we have today, with high concentrations of nitrogen and oxygen and much lower concentrations of the reduced compounds that made up a larger percentage of the early atmosphere. Over the next 2 billion years, oxygen concentrations continued to rise as photosynthetic organisms spread across the Earth. Oxygen concentrations probably reached current levels of around 21% 400 or 500 million years ago. The availability of oxygen in the atmosphere led over time to the diversity of life we see around us today. The widespread photosynthesis that produced the oxygen also led to a slow and steady removal of carbon dioxide from the atmosphere as carbon plants converted to living material became trapped in the ground, in a number of forms including limestone, peat, and the oil, coal, and natural gas we are now returning to the atmosphere through industrial activity.